Hello, my dear VLSI aspirants. Welcome to Deep Silicon VLSI YouTube channel. In this video, we mainly focus on complements. What are the complements? Why do you need them? Which one is the best? We want to know. Let's continue. Actually, complements are used to represent negative numbers. Remember, coming to a complements, every number system has two types of complements. They are r minus 1's complement, r's complement. I repeat, a particular number system whose radix value is r has two types of complements. They are r minus 1's complement, r's complement. For example, let us consider binary. Therefore, radix value is 2. Hence, the binary number system has 1's complement and 2's complement. Remember, okay? R minus 1, 2 minus 1's complement. Similarly, 2's complement. Similarly, if you take octal, then you get 7's complement. Similarly, 8's complement. Okay, guys? As usual, if you take decimal, 9's complement, 10's complement. Hexadecimal, F's complement, 16's complement. Of course, F's complement is also called as 15's complement. Now, how to find out the R's complement? Okay, coming to the R's complement, there is only one step. That's it. No more other things, other procedures. That is, if you take r minus 1's complement, that's only one step. That is, you need to subtract the given number from the maximum possible value present in the number system. Suppose if it is like binary, let's assume, then r minus 1's complement will be 1's complement. Suppose we want to find out 1001. For this binary number base 2 number system, we want to find out 1's complement. If it is radix value is 2, they are asking 1's complement, then obviously it is r minus 1's complement only. So they are asking us r minus 1's complement. What is the procedure? You need to subtract this number from the maximum possible value present in the binary number system. What is the maximum possible value present in the number system? Binary, 1 only, because in binary radix value is 2. Hence, the symbols are 0, 1. Isn't it? Yes, every number system has the symbols 0 to r minus 1, 2 minus 1, 1, 0, 1. Hence, in binary number system, the maximum possible value is 1. You need to subtract this from the 1. That's it. So, here we need to take 1, 1, 1, 1, 1, 0, 0, 1. Then it is 0, 1, 1, 0. Hence, guys, everybody see here, the 1's complement of 1001 base 2 is 0110. Simply by saying that, you can tell, like replacing 1 as 0, 0 as 1. If somebody asks you in VLSI interviews, why are you taking 0 as 1, 1 as 0? Then thumbs up. So guys, please remember the approach. Not like 1s are 0, 0 or 1 like that. For example, if you ask me for this octal, or else let's take hexadecimal, the r minus 1's complement will be f's complement or 15's complement. For example, we want to find out BA. For this hexadecimal number, we want to find out the r minus 1's complement, which is f's complement. What is the procedure? You need to subtract the like this number from the maximum possible value. That's it. So what is the maximum possible in hexadecimal? F only. So you need to subtract this BA from F. So let's do this. For example, let's take this F. Okay, you write down BA, right? So here F 15, A 10. I given the shortcut also, B C D E F. Okay, so A means 10, B means 11. 15 minus 11, 4. 15 minus 10, sorry guys, 5. 15 minus 11, 4. 15 minus 10, 5, 4. So the r minus the f's complement of the hexadecimal number BA is 4545. This is the procedure and approach to calculate, to determine the r minus 1's complement of any number system. Any number system, just you need to subtract from the maximum possible value present in that number system. Okay, now it's time to discuss about r's complement. Is it r's complement or r minus 1's complement? How you decide? They will give us the radix. If the radix is 2, then 1's complement will be r minus 1 only. If it is 1002 base 1001 base 2, if they ask you calculate the 2's complement, then it is r's complement only. Remember, a number system has two types of complements only, that is r minus 1's complement, r's complement. Why I am stressing this means, suppose if the question says 3's complement of 1001110 base 2, is this question valid? No. A binary whose radix value is 2 has only two types of complements. R minus 1's complement, 1's complement, or 2's complement. You don't get any 3's complement. Remember, in this way in VLSI interviews they may stress, can you calculate 3's complement? Do you know the procedure? Like that. They will test your logical knowledge. Okay, let's start r's complement of all the number systems. Let's start. Coming to r's complement, let's say binary. Then r's complement will be 2's complement. The procedure is, it contains two steps. Step 1, same as r minus 1's complement. Whatever we have done in r minus 1's complement, we need to perform as it is. Got it? And step 2, we need to add 1. Add 1 to the least significant digit. Why I am telling LST? Why don't you tell B? In the sense, if it is binary, we will call it as bit, binary digit. It is not like always binary. It may be octal, decimal, hexadecimal. Hence, you need to say LSD only, least significant digit. Let us start. The first one, 1001. 1001. Then here, step 1, perform 1's complement. Therefore, if you subtract it, you will get 0110. And step 2, we need to add it. And while you are adding here, we get like 1, 1, 1, 0. This one. So 0111 is the 2's complement number for 1001 base 2 number. Got it? This is what for binary. Similarly, let us take hexadecimal. We want to calculate 16's complement. For 16's complement, step 1, obviously F's complement. We got 4545. Step 2, we need to add 1 to the least significant bit. Therefore, it is 6454. This one. Hence, guys, the 16th complement of BA base 16 is 4546. This is the procedure to calculate, to determine F's complement, R minus 1's complement or R's complement. This is only the procedure. Then you can calculate 3's complement, 4's complement, 5's complement, 6's complement, any complement. Remember, a number system has only two complements, R minus 1's complement, R's complement. Okay, they may test you in interviews. Can you calculate 8's complement for 1003 base 10? For base 10, 8's complement is possible? No. For a decimal, only 9's complement or 10's complement. Follow this procedure to calculate R minus 1's complement and R's complement of a particular number system whose radix is R. Okay? Let's continue the examples on complements. Question number 24. The tens complement of 25.639 base 10 is 74.360, 75.360, 75.361, 74.361. See, the base value is 10 and they are asking us tens complement. Therefore, they are asking us R's complement. What is the procedure for the R's complement? Is it 2 steps or 1 step? 2 steps. For the R's complement, first you need to find out R minus 1's complement and then you need to add 1 to the least significant digit. Okay, wantedly I have taken decimal point. Okay, let's start. Here in decimal, the maximum possible value is 9. You need to subtract the given number from 9. Hence, we are taking 99.999. It is 25.639. Let's subtract, that is 9 minus 9, 0. 9 minus 3, 6. 9 minus 6, 3. 9 minus 5, 4. 9 minus 2, 7. It's 74.360. It's fine. But what's next step? Step 2. Add 1 to the least significant digit. So you add 1 below 4 or below 0? Below 0. Least significant digit, whatever the decimal point or integer values, you need to take the least significant digit. Hence, you add 1 here. Therefore, it is 74.361. Hence, the tens complement of 25.639 base 10 is 74.361. 74.361. Option D is the right answer. Now, let's have question number 25. Obtain 4's complement of 3210 base 4 means radix value is 4. They are asking 4's complement. R's complement only. Calculate R minus 1's complement, 3's complement and then add 1. That's it. So, this one maximum possible value in base 4 number system is 3. So subtract 3. 3, 3, 3, 3. It's a 3210. Hence, it's a 3210. This is the 3's complement. But we want 4's complement. Now, add 1 to the least significant digit. Therefore, here this 3 plus 1, what you get, guys? Actually it is 4, but in base 4 number system it is 10. 4 power 0, 4 power 1. Therefore, 1 into 4 power 1, 0 into 4 power 0. It's 4 only. Hence, it's a 3, 1. It's a base 4 number system addition. So, you get 1, 0. Again, 2 plus 1, 3, 1, 0. Hence, guys, 4's complement of 3210 is 0130. This is the what base 4 number system 4's complement. Now there is a last question, that is 2's complement of 100 101 base 3. What is the answer for this? Please comment below if you know the answer. Okay, in this video we are going to discuss about 2's complement representation. Suppose if there is a decimal number, how to convert it into 2's complement representation. Similarly, if we have a 2's complement representation, how to convert it into back the decimal representation. Let's see in detail. Without any delay, let us start. Question number 26. The 2's complement representation of minus 541 in hexadecimal is DEE, DDD, DEF, DE3. If you see the solution about this question, it has two stages. Stage 1. First, you convert the decimal number into 2's complement representation. Once it is done, in stage 2, we need to convert that 2's complement representation into hexadecimal form because the options are in hexadecimal form. Okay, let's talk about stage 1. How to convert a decimal number into 2's complement representation. It has two steps. Let's take them. Step 1. Even though they asked for negative number, we need to represent in step 1 positive number only. Represent 541 base 10 in binary, including sign bit. Okay, we know very well the sign bit is 0 for positive numbers, 1 for negative numbers. Here it is 541. In step 1 we take positive number only. Hence here first of all we want 541 in binary. Let's start. This is 541. If you convert it into binary, it is like this. So guys, the 541 in decimal, in binary as this, like 1 000 0 0 1 0 1, this one, and we need to mention even including sign bit. We know very well sign bit is 0 for positive numbers and 1 for negative numbers. Okay, now here we need to take the sign bit. Here you can take sign bit, fine, but here there is a noteworthy point, that is the options you see, each hexadecimal digit can be represented in 4 binary bits. 3 hexadecimal digits are there, then how many bits? It has 12 bits. But guys, as per the decimal number including sign bit, how many bits we have right now? 4, 8, 9, 10, 11. We have only 11 bits. But he is asking in 12 bits. Then as per the options, here we require 12 bits. Hence, what we have to do is, how many the extra bits we require. You need to place that many zeros between the sign bit and the magnitude bits. This is magnitude bits, this is sign bit. Hence here we have 11 bits but we want 12 bits. Then how many bits you require extra? 1 bit you require. So you need to add 1 0 between the sign bit and the magnitude bits. That is simply 0. For better understanding purpose, I took black color. So now we have 12 bits. Hence, step 1 completed. Then step 2. What is step 2? Apply 2's complement representation to the step 1. Apply 2's complement. Okay. So you know very well 2's complement representation. You need to find out the 1's complement for this and you need to add 1, and there is a shortcut also. What is that? You take the ones like the original binary sequence from LSB to MSB. If you get zeros, you copy the zeros as it is and you copy the first logic one also. After first logic 1, then replace 1 with 0, 0 with 1. That means apply 1's complement. That's it. So here from the LSB, we don't have any zeros. Leave it. First logic 1 is there. So you take it as it is. 1. You copy it as it is. Then for the remaining bits, apply 1's complement. Means 0 to 1, 1 as 0. So that it is 1, 0, 0, 0, 4 ones, 0, 1, 1. This is the 2's complement representation. So stage 1 completed. We got the 2's complement representation for this decimal number completed. Now what next? If the options contains 1s and 0s like this, the problem is over. But still options are not in binary sequence. Hence we want to convert this binary sequence into hexadecimal form. We already studied from the previous videos. You group 4 binary bits to make one hexadecimal digit. Therefore here we can take this. That is 0011, 3. This one 1110. Then what it is, guys? 8 plus 4 plus 2. 12 plus 2, 14. That is B, C, D, E. So it is E. Similarly, 1101. 12 plus 1, 13. Means D. DE3. Hence guys, minus 541 base 10, the decimal number in 2's complement representation in the form of hexadecimal is DE3. Okay. Let's see another question. 27. 2's complement representation of a 16-bit number, 1 sign bit and 15 magnitude bits is FFFF. Its magnitude in decimal representation is 0, minus 1, 32, 767, 65, 535. This question tells about how to convert a 2's complement representation into decimal representation. Exactly opposite to the previous question. Okay, then how? What is the procedure to convert a 2's complement number into decimal representation? Guys, the procedure is very easy. It contains, let's consider here the procedure. We need to see MSB first of all. If MSB is 1, then remember guys, it is a negative number. The given number, whatever you are getting, the decimal number, the final decimal number will be negative only. It is negative number and apply 2's complement to get answer, to get final answer. Okay, so this is what the procedure to convert a 2's complement number into decimal representation. In our sequence, whatever the MSB is 1, then it's a negative number. You want the answer, the final answer, then you apply 2's complement again to get the final answer. This is the procedure. Whereas if MSB is 0, let's assume, then what is the procedure? If MSB is 0, it is a positive number. Then you just convert into binary to decimal here, so that you will get the answer easily. I mean to say, no need to apply 2's complement to get the final answer. That's it. So let me write it. If MSB is equals to 0, then it is a positive number and convert it into binary, convert it into decimal to get final answer. That's it. Okay, this is the procedure to convert a 2's complement number into the decimal representation. Now guys, it is FF only na. Let me write this. That is like 1 1 1 1 1 1 1 1 1 1 1 1 F of course. One more. F. Now what to do? Check MSB. MSB is 1. Then it is a negative number. Hence, option A is not right answer. Option C is not right answer. Option D is also not right answer. Then you want decimal number, na? What is that number? So to get that number, first apply 2's complement. Again convert into the decimal. Okay. Now let's do this. What is the procedure to convert like this one into 2's complement representation? Again apply 2's complement again. Therefore the procedure we know very well already. This is 1 and remaining all zeros only. Just 1's complement. This. That's it guys. So here I can say that by applying the 2's complement like 2's complement again, then we got 4 zeros, 4 zeros, 4 zeros, 3 zeros, 1. And now again you convert this into decimal. To get the final answer you convert into decimal. Then what is the value guys? 1. So answer is 1. But at the beginning itself we told if MSB is 1, then it's a negative number only. It is a negative number only. Hence FF is in the 2's complement representation. That a number is represented in the 2's complement representation as FF. And its decimal representation, decimal value is -1. Option B is the right answer. Got it? In this video, we are going to discuss about 2's complement extension. Let's see the question. Number 28. A number in 4-bit 2's complement representation is x3, x2, x1, x0. This number, when stored using 8 bits, will be 4 zeros x3, x2, x1, x0. 4 ones x3, x2, x1, x0, x3 4 times, x3, x2, x1, x0, x3 bar 4 times, x3, x2, x1, x0. The question is very simple. Suppose some decimal number is represented in 2's complement using 4 bits. I want to use 8 bits to store the same number. Then how it will be? Are you taking MSB, the higher order byte, higher order nibble as 4 zeros or 4 ones or x3 only or x3 bar? That we need to find out. Yes. Now let's assume here the number can be positive or negative. You cannot restrict. He didn't say negative number, positive number like that. It could be either positive or negative. Let's assume case 1 positive number. If it is positive number, what is the procedure? How you can use 4 bits and 8 bits, etc. Let's consider plus 7. This is your decimal number. Then what is the 2's complement representation for this plus 7? Only step 1. You need to consider plus 7 including sign bit in binary. That's it. 7, 1, 1, 1. These are magnitude bits. And including sign bit you need to mention. That is 0. 0 is the sign bit. And these ones called magnitude bits. Okay. Now we want to convert into 8 bits. I want to use 8 bits. Then what to do? It's very simple. It is like how many bits you want to represent, you can represent. The thing is, you need to place that many number of zeros between the sign bit and the magnitude bits. That is itself is the procedure. So here let's take sign bit 0, magnitude bits 1, 1, 1, and you need to keep the zeros between the sign bit and the magnitude bits. How many bits you want to storage? Using 8 bits now. Then here already 4 bits are there. Then how 4 more bits are required. You take 4 more zeros. This. So that guys, the number whatever 0, 1, 1 using 4 bits can be stored as 0, 0, 0, 0, 0, 1, 1 in 8-bit format. Then we all think 4 zeros, option A is the right answer. No, the solution is not yet over. You assumed case 1 positive. What if it is a negative number? Could be possible. Hence, we want to consider that as case 2 negative number. It's minus 7. What is the procedure for representation of negative numbers? It is a 2-step procedure. That is, first step, you need to represent plus 7 including sign bit. It is like binary sequence 1, 1, 1 and the sign bit 0 only, because in step 1 we consider plus 7 only. Yes, this is step 1. It is not yet completed. Step 1 completed. What is step 2? We want to apply 2's complement to this. Okay. Therefore, here apply 2's complement. You get 1, 0, 0, 1. This is the 2's complement representation for the minus 7. That is 1, 0, 0, 1. This is about 4 bits. But we want to store 8 bits now. Then what is the procedure? It is like I have told you in the step 1 itself. You need to place the zeros. How many bits you want to represent? That many you can add. But remember, you need to place the zeros between the sign bit and the magnitude of the bits. Then here this is the sign bit. So it's a 0 and it is 1, 1, 1, 1. 1, 1, 1. Then we are placing here 4 zeros because we want to represent it in 8 bits. Step 1 over. Now step 2. What is the step 2 guys? Simply apply 2's complement. That's what we did here also. Apply 2's complement, then copy one as it is and then apply 1's complement. Therefore, it is like this. So now just I am segregating, concluding. Plus 7 using 4 bits is 0111. Using 8 bits is 5 zeros 111. Similarly, minus 7 using 4 bits 1001. Using 8 bits one like a 5 triple like 5 ones 001. And you see here guys, that is 0111, right? Here also 0111. And this MSB only copied here. Yes. Whereas you see here, the number is 1001. Here also 1001. And the MSB also here copied. This one. So the conclusion is, if there is a number in 2's complement representation as x3, x2, x1, x0, in 8 bits, the representation will be like the MSB only copied. Okay, so this is the MSB for 4 bits, right? So x3, 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 x2, x1, x0. So this is the procedure to convert a 2's complement number in 4 bits into a 2's complement number in 8 bits format. So what is the answer? That is none other than option C. Okay. Let's see another question. A number n is stored in a 4-bit 2's complement representation as A3, A2, A1, A0. It is copied into 6-bit register and after a few operations, the final bit pattern is A3, A3, A2, A1, A0, 1. The value of the bit pattern in 2's complement representation is given in terms of the original number n as 32a3 plus 2n plus 1, 32a3 minus 2n minus 1, 2n minus 1, 2n plus 1. The input pattern is a3, a2, a1, a0 and some operations have done. Final bit pattern is a3, a3, a2, a1, a0, 1. Guys, here it's very simple. A 4-bit pattern converted into 6-bit pattern. That's it. From the previous example, what we understand, a number in 2's complement representation in 4 bits can be extended into 8 bits by simply copying the MSB. That's it, what we learned. Now, in the same way, you take this bit pattern and you convert it into 6-bit pattern, this, where there are 6 bits, A3, actually let's assume here A3, A2, A1, A0. Now we are copying the MSB into remaining 2 bits. It's A3, A3 only. By doing so, value going to change? No, the value is same. That number is n only. It is n only. Now, here by checking the output bit pattern, here what we can think is shift left operation, shift right operation. Let's consider 0, 1, 0, 0. You do shift left so that this 1 will appear here, 0, 0. Yes. And here the fresh bit will appear 0. Now, what is the original value, guys? 4. What is this value? 8. Means if you do shift left operation, value is going to be multiplied by 2. Similarly, if you take 0, 1, 0, 0, if you do shift right operation, means here 0, 1, 0. Now the fresh 0 will appear here. Now what is the value? It is 2 only. Means during shift left operation, value is getting multiplied by 2 if you do shift left operation for one time. Similarly, shift right operation one time, the value gets divided by 2 one time. So let's assume this is k, this will be 2k. This is k, this will be k by 2. This one. Okay. Now with the same pattern, what we do is we will do shift left operation, because here A3 only. Hence we are taking the same content and now we are doing shift left operation. So here this A3 will appear here, this A3 here, A2, A1, A0, 0, like this happened, right? This 0. Because of this, what's the value gets multiplied by 2n. So it's a 2 into n. By doing shift left operation, the original value gets multiplied by 2. So this is the value. Right. Now again check with the output bit pattern. Output bit pattern, there is in place of 0 there is a 1. Let's consider here this number as it is. If we add 1, let's consider here A3, A2, A1, A0, 0. Again here A3. Here if you take this, add 1, then it's 1, A0, A1, A2, A3, A3, this one. So the value get added by 1, so that here the bit pattern will be in this way. The same here 6-bit register. Therefore this is A3, A3, A2, A1, A0, and then placed here 1. That means that value get added by 1. This one, this is what here the final bit pattern it is now matched with the output bit pattern. So first of all, here we have done the copy the MSB into the remaining two fields. Because of that, value is not going to change, it is still n only. If you do shift left operation for one time, this will be A3, A3, A2, A1, A0, 0. So that the value gets multiplied by 2. Similarly, if you add 1 to this bit sequence, you will get A3, A3, A2, A1, A0, 1. That means 2n plus 1. This 4-bit 2's complement representation converted into 6-bit 2's complement representation. If it wants to happen in this way, the operations are, first we copied the MSB and then we have done shift left operation and then we have added 1. So as per the options, the right answer is option D, 2n plus 1. Okay guys, this is what about 2's complement representation extension. If we have a representation in 4 bits, we want to extend it into 8 bits. How you can extend the 2's complement representation? This is what the question is. This video gives you the clear representation regarding 1's complement. Let's see the question. Which one of the following is the correct answer when 11011 base 2 is subtracted from 11101 base 2 by using 1's complement method? There are the options. Guys, first of all, there is one decimal number. How you can represent in 1's complement, we need to know, because this is 11011 in 1's complement. What is the decimal number? You should know. For that reason, let's have this. For example, it is plus 6. Then the procedure is, we want to represent the plus 6 using 1's complement representation as, first you convert this 6 into binary. That will be 1 1 0, and you use the sign bit. Sign bit is 0. This is sign bit and that is magnitude. That's it. Sir, it is 1's complement. No, you need to apply 1's complement. No. In 1's complement representation also, for positive numbers, you need to represent the magnitude including the sign bit. We know sign bit is 0 for the positive numbers, 1 for negative numbers. It is plus 6 only, and it is 0 1 1 0. If at all they want to represent the plus 6 using 6 bits, let's assume, then the magnitude bits take 1 1 0, the sign bit 0. In between the sign bit and magnitude bits, you can add any number of 0 as per your requirement. You want to convert these 4 bits into 6 bits, right? Then add 2 bits, this one, so that now you got 6 bits. In this video, we are going to discuss about sign magnitude representation, 1's complement representation and 2's complement representation using a simple example. Let's start. P, Q and R are the decimal integers corresponding to the 4-bit binary number 1000, 1100, considered in sign magnitude, 1's complement and 2's complement representations respectively. The 6-bit 2's complement representation of P plus Q plus R is, first of all, we want to find out what is P in decimal number. They said P is sign magnitude representation. Therefore, if it is 1100, the MSB represents sign bit. It's 1, means it's a negative number. And you take the magnitude, because usually in sign magnitude representation, the MSB will be the sign information and the remaining bits regarding the magnitude. That's it. That's what the procedure. Fine. So it is like this is in decimal 4. It's -4. Done. Now you take the Q. What is Q? It is in 1's complement representation. You take 1100 only. This is your 1's complement representation. Now you do one thing. This is 1100. Calculate the decimal representation as per the 1's complement representation. Usually the procedure is, if MSB is 1, it's a negative number. If MSB is 1, it is a negative number representation. You want the decimal number, then apply again 1's complement representation and then convert into decimal. So if you convert this into, again apply 1's complement, you will get 0 0, you will get 1 1 0 0. Then guys, if you convert this into decimal, you will get 3, that means -3. Again, R is regarding the 2's complement representation. The number is 1100. As usual, MSB represents the sign. See, MSB is 1, then it is a negative number. If it is a negative number, apply again 2's complement to this and convert it into decimal. That's it. So apply again 2's complement. It is 0 0 1 0. Now you convert this into decimal. What is that? 4. Hence it's -4. So guys, finally, as per the given representation, we've calculated PQR. P is 4 minus 3, R is equals to -4. You add them, P plus Q plus R. It is like -8 -11, right? -11. We want to see this -11 in 2's complement, because the question says the 6-bit 2's complement representation. Okay, -11. What is the procedure? It is a negative number. Therefore, it has 2 steps. That is, step 1. Even though he asked for negative number, we want to represent in positive numbers only. The sign bit for positive 0 and that 11 in magnitude representation, it is like 1011. Right, this is magnitude and this is sign bit, but here they asked for 6 bits, but here we got only 5 bits now. So here what you can do is, between the sign bit and the magnitude bits, you can add any number of bits as per your requirement. That's it. I want 6 bits, hence here I am adding 10 between the sign bit and the magnitude. Now step 1 over. Now what is step 2? Simply apply 2's complement. By applying 2's complement, here it is 1 0 1 0 1 1. So it is 1 1 0 1 0 1. The 6-bit 2's complement representation of P plus Q plus R is 1 1 0 1 0 1. In this way, you can represent any decimal number in a sign magnitude representation, 1's complement representation, 2's complement representation. Okay guys, I hope you like the video. Please subscribe our YouTube channel. Hello my dear VLSI aspirants. Welcome to Deep Silicon VLSI YouTube channel. In this video, we are going to discuss about 2's complement representation and beyond that. Yes, this is one of the best question to challenge your ability in 2's complement representation. Let's dive into the question. Number 34. P is a 16-bit integer. The 2's complement representation of P is F87B base 16. The 2's complement representation of 8 into P is C3D8, 187B, F878, 987B base 16. Guys, every question has different solutions. Every problem has different solutions. Likewise, even this question also has 2 different solutions. Let's see method 1, the first one. Here he told P is a 16-bit integer and the 2's complement representation of that P is F87B. Now let's find out the binary representation. If it is F87B, the binary representation is 1111 1000 0111 1011. This is the 2's complement representation in binary sequence. Guys, how to find out the decimal value of this? Because you need to do 8 into P now. If you have the P value in decimal, so that you can multiply and you can tell the decimal value. Of course, again we will convert into 2's complement. Anyway, he is asking the 2's complement representation of 8 into P. Now, if you take this and MSB, if MSB is 1, what it is? It is a negative number. And if you want to get the decimal value, apply one more time 2's complement, then convert into decimal. If you do that, means if you apply 2's complement here, it's 1 0 1 0 0 0 0 1 1 1 1 0 0 0 0 0. This is now in like the true form. Then you convert into decimal. The value is 1925, 1925 base 10. Now guys, what to do? Now you got the P value. Next, we need to do 8 into P. 8 into P. What is that? 8 into minus 1925, 1925 base 10. Then the answer will be like the decimal value minus 15400. This one. Now you got the decimal value. Now we need to convert this into 2's complement because he is asking 2's complement representation. Now if you take this, it's a negative number now. Therefore here it requires 2 steps. We need to write the magnitude bits along with the sign bit 0. Because it's a negative, it requires 2 steps. Again for that we need to apply 2's complement including sign bit. Then means here you convert this 15400 into binary including sign bit. If you represent, then the binary sequence is like 0 0 1 1, 1 1 0 0, 0 0 1 0, 1 triple 0. This is the one. This is the sign bit, and here if you take this again into magnitude, this is a magnitude information regarding 15400, right? As the options contains 16 bits, because 4 hexadecimal digits are there, so that here you require this 0 between the sign bit and the magnitude bits. Fine, we got this. Again we need to apply 1's complement, 2's complement. Therefore it is like 0 0 0 1, then 1 0 1 1, 1 1 0 0, 0 0 1 1. This one, guys. So we got the 2's complement representation of minus 15400 base 10. Now in the options hexadecimal, right? Then again you convert into hexadecimal. Therefore it is C, and again it is 3 D 8. So guys, everybody, the 15,400 minus 15,400, which is 8 into P in 2's complement representation in terms of hexadecimal form, is C3D8. Hence the right answer is option A, C3D8. But guys, you only like observe how many efforts we have to put to reach the answer. You need to convert into decimal, again you need to multiply, again you need to convert into magnitude. 15,400, how much time it will take? Again getting the 2's complement, again converting into hexadecimal. This is method 1. Let's see method 2. Guys, here what is the P in 2's complement form? F87B. Let's convert into binary. Therefore it is 1 1 1 1, 1 triple 0, 0 triple 1, 1 0 1 1. Right? Now guys, you know shift left operation, shift right operation. Let's consider 0 0 0 1. Now you do shift left operation one time. Then what you get? This 0 go outside, this 0 will come here, here, this 1 will come here, and the new 0 will be added. It is 2. If the decimal value is 1, the decimal value is 2. Means here, if there is a binary sequence, if you do shift left operation one time, the value gets multiplied by 2. Similarly, you do another time, so that the 0 goes outside, so that 0 1 0, here 0 will be added, the new 0. Then what is the value? 4. What I mean, guys, for a particular binary sequence, if you do shift left one time, then the value gets multiplied by 2. 2 times, the value gets multiplied by 4, means 2 power 2. So here, based on that concept, we can give the solution here in fraction of seconds. Yes. Now here what he told, 8 into P, na? So let's write 8 into P. This 8 into P can be written as 2 power 3 into P only, na? Yes. If you want to multiply the P value into 2 power 3, it is similar to performing shift left operation 3 times. Yes, that is equal to 2 power 3 into P only. Now let's take this sequence. You do shift left one time. Therefore this one go outside, so that it is 1 1 1, and this one will be added here. Again here 0 0 0 0, 1 1 1 1, 0 1 1. The fresh 0 will be added as LSB. So it is equal to 2 power 1 into P. Okay guys, again here you do shift left one more time. Here 1 1 1 0, 0 0 0 1, 1 1 1 0, 1 1 0. Again one more fresh 0 will be added. It is equal to 2 power 2, because till now 2 times shift left has been done. then it is 2 power 2 into P. So finally guys, one more time shift left, so that it is 1 1 0 0 0 0 1 1 1 1 0 1 1 0 0. A fresh 0 will be added here. It is equal to 2 power 3 into P, because for the P sequence we have done shift left 3 times. Finally we got this sequence. Now here if you convert into hexadecimal form, you will get the answer, because we didn't go away from the 2's complement to decimal again. No, we are still in 2's complement only. Of course we have performed like shift left operation. Now when you take it into hexadecimal form, 1100 C3D8 in hexadecimal, C3D8 option, like base 16. In this way guys, we can complete this particular question in a fraction of seconds. You need to know this hack definitely, because guys in off-campus placements they conduct some hiring test. In that test paper, definitely you can expect these kind of questions. It may look huge, but it requires very less amount of time if you know the tricks how to solve them, right? So this is what regarding the 2's complement representation, much more. See you in the next video. This is Shivaram signing off. Jai Hind.